So this is the way that I've kind of structured this talk is almost like a toolkit I'm trying to provide. So I'm not going to talk about my own research, but I'm talking about methods that have sort of been used in physics that I'm going to try to generalize and hopefully make it accessible to as many people here as I can. So I have examples from all over, including some stuff that we did during the summer school. But if there's anything that's confusing or seems useless, absolutely, like, raise your hand and say to me, this sounds useless. Okay, I'll keep going. So,
the robustness of the machine is emerging.
Yeah. So I think one kind of robustness that people talk about is robust systems. And roughly speaking, this means that when you give it a push, it springs back. So here there's a evolutionary walker. So they have some muscle model, and the position of the muscles are evolved, and the poses are evolved, and they chain together the poses, and they find that they can have this thing walking around and throw, bowling balls at it, and it won't fall over when they're done. And that's a rabbit. When you push it, it doesn't die. Nothing really bad happens to it if you don't push it, too hard. But another kind of robustness is the idea of a robust theory. And for that, I kind of need to define what I mean by pushing a theory. So any theory is incomplete. And the thing is that we're going to be making tons and tons of errors whenever we write down any kind of abstraction about the world. So pushing a theory is just making some kind of error. And then you can ask, do you still get the same kind of result? And there is a big, big question here of what exactly does the same mean, and it's different for different questions people might want to ask or for different uses of the theory. Okay, no pointer, so I'll use my hand. But yeah, basically, if this didn't happen, if any error completely wrecked a theory, we wouldn't be able to do science, because we're inevitably going to make some kind of error. And so then if everything stops working, well, where does that leave us? We can't confirm anything, we can't use anything. So there's a bunch of the people have observed this in various kinds of fields. So there was a paper by Wigner about the unreasonable effectiveness of mathematics. Why does the ratio of the circumference of a circle to its area show up in the dynamics of populations? And why should we, this should be a surprise. We should really be shocked that all of these things tie together in ways that we wouldn't expect. Then a number of blog posts and other articles, the unreasonable effectiveness of science, the unreasonable effectiveness of deep learning. Why does this one kind of paradigm seem to work on all sorts of different problems? And even the unreasonable effectiveness of recurrent neural networks, a more recent one, where you throw some C code into a neural network and it seems to learn C syntax without you having to do very much to it. Why should you expect this very generic system where you didn't put any information about the structure of language or the structure of C code or the structure of Shakespeare, why should it actually be able to work? So there are a couple of more concrete examples. One big source of examples is population dynamics, because the populations are made of individual organisms, and each individual organism can be very different if you look at it in detail. So you can have, a lynx hair system, or I think this is a paramecium and didymum, which eats it. E. coli and lambdaphage, and this is actually something that I'm kind of pushing from my advisor's research group, where they recently did a paper on how you can use population dynamics to explain the difference between turbulent flow in a pipe and the zonal flow at the edge of the pipe that kind of circulates around, where the one kind of eats the other. And it turns out that that works pretty well to describe the turbulence transition. And I mean, this is water in a pipe, and this is a lynx. And that's very different, right, if I look at it in detail. But I can boil all of this down into a model, and these are the only equations in my talk, so please don't worry. Which is very simple, and it predicts things like the oscillations, it predicts the phase lag in the oscillations. And it seems to work, despite the fact that I've thrown out almost everything about the things that make up this model, and I've just described them as two populations, X and Y. Another example is in crowd dynamics. So crowds are made up of people. People, some people are physicists, some people are philosophers, some people are artists, people have different childhoods, different life histories, different different emotions, even different goals that they want to do in behaving in a crowd. When they're at a shopping mall, they want to buy different products or things like that. But when the density gets very high, then people basically behave like this, where the constraint is they can't move through each other, and that determines a large amount of the information about how the behavior at the plug proceeds. And so all of these details about people kind of wash away. And it turns out you can also get a similar thing with cars. So there's this phenomenon called traffic waves, where you can have some traffic accident that creates a local increase in the density, and then cars essentially can't move through each other. So even when the accident is gone, that local increase of the density continues to propagate, and it sits in the same location for hours after the accident, and it just looks like it's sitting there, this standing wave. They can move forward or backward depending on conditions. You can even mess with them by intentionally driving slowly. You can kind of dissipate them intentionally. But it's still this, basically. So the point is that these simple models seem to have the ability to generalize somehow, that they're capturing something about the more detailed systems, that when you put a lot of these detailed components together, that thing, whatever it is that they're capturing, is the thing that's coming to the fore. That's the thing that's dominating the phenomena that occur. And it might not be that the systems will be dominated by that in every regime, but it does seem like that thing that comes to the fore is shared by a lot of different systems. A lot of different agents, a lot of different objects often have the same kind of thing. And then when you enhance that, then you find that actually they can all be described in the same way. And therefore you get this kind of generalization. But the other thing about this is only the collective behavior is robust. So if I look at the traffic waves, I can use simple equations to talk about those as solitons. I can look at that in other soliton systems as well. But I can't talk about the performance of the engine of one of the cars from that level of model. That's not going to actually be preserved at that level of description. So there's kind of this effect is, in physics, there's a sort of a saying 1 to infinity, which is that we can solve systems that have one object, we can solve systems that have two objects, and then we can't do anything until we get back to infinity. And that's kind of interesting, but it's part of this generalization. When you have a very large number of things, the collective behaviors are what matter. So there's this n-body problem where if I have one gravitating body, it just sits there, it's trivial. If I have two gravitating bodies, I can assign this to an undergrad, and they can usually solve it if they have some priming for it. It's not so hard. But if I have three bodies, then 350 years and generations of physicists can't solve it in general. We have some special cases. I think even recently there have been new special cases that people have been publishing on the three-body problem. You can basically, this is a rabbit hole you can go really deep into, and there's provably no general solution. But when you go to infinite bodies, then you get statistical mechanics, and it works really well. And it's not hard. I mean, it's at the undergrad level. An undergrad physics student takes a stat mech course and has to derive things about gases and liquids and things like that. So somehow, when I get this big, there's some new numbers that describe my system, or some new qualities that describe my system, and those qualities are sufficient to describe the system, at least at that coarse scale. I lose the details of the microscopic motion. If I needed to care about what each water molecule in here was doing, I would be lost. It would just be the three-body problem again. But somehow I don't have to care anymore when I get big enough. So it's kind of weird, but the emergent properties, things like the flow of water, the wetness of water, surface tension, things like that, they're simpler than the stuff that makes it up.
It seems like to me you're changing the sort of the what do you mean by easy or difficult in the case of three and this water molecule? Is it correct to say?
So
like in the case of three, you tried to actually predict the exact motion, right? But in this case, it's the sum of the order of motion roughly. So if you just want to estimate the sum of the three body in a really rough scale, as is to 23 scale, is it equally easy?
So later in my talk, I'm actually going to step through scales on a certain system and see what happens if I hold myself to the constraint. I only predict things on the scale that I observe. So I take observations at a given scale, and then I predict things on the same scale. And what will happen, at least in the case of the water, is that the prediction gets harder and then it gets easier. So if I look at it on a very coarse scale, I still need something like Navier-Stokes, but I can to predict the actual fluid motion. But I can actually, in some sense, do that. So I guess what I would kind of get, maybe this is the one. It's not really a definition, but the one observation in my talk about sort of definitional things is that when we have this kind of emergent phenomenon, it seems like the characteristic of that is that there's some new degrees of freedom that are appropriate after the emergence compared to before.
Sorry, can I ask you for just some...
Okay.
If so, someone who doesn't know anything about this and is
sure.
not used to any mathematics, can you just explain what degrees of freedom mean?
Yeah. So in the three-body problem, each particle can have a position, it can have a velocity at each moment in time. So those are things that can vary. So you need to be able to predict how those things that can vary change in order to predict the future of the system. If I have an error on one of them, that affects my ability to predict the system's future. For something like the water, the point is I no longer need to know the individual positions and velocities of every water molecule. I can instead say, I'm going to take a lump of water and ask what's the average position of the water here? What's the average velocity of the water here? And it turns out that that allows me to predict the future of the system actually better than if I had tried to do it with the individual water molecules, in part because of practical considerations of simulating a very large number and making a lot of errors versus simulating a small number of things. But essentially, it's the things that can vary in a way that matters for the future of the system, I would say.
Because I understood all you said, apart from I still don't know what degrees of freedom is.
Okay. So like do you mean in general or in the specific case?
Just so zero knowledge,
Yeah.
zero knowledge. I understood that, okay, when it comes to the prediction of the water, you cannot just look at the behavior of single molecules. You have to, you talk about emergent behavior. But so what's degree of freedom here?
For water, or?
In the context you're talking.
Maybe roughly, it's like how many numbers you need to describe this.
Yeah.
To describe the water.
To describe the system you want.
Yeah, water or crowds or the brain if you're trying to do the brain or whatever.
Okay.
But it's the sort of the number of different things that you need to know in order to talk about what it will do.
So that's degrees of freedom?
Yeah,
Okay.
because they're things that they're free to vary in some sense. You can take all of their different values and you have to deal with that.
So maybe add just 3 words to this. The idea is that it can be the same system, but it can exist in several states. And so then, point, how many numbers do I have to give you to enable you to tell which of the states it's in?
Yeah. So, in some sense, dealing with the water from the point of view of water is a lot easier than dealing with the water from the point of view of molecules. And that's a consequence of sort of the emergent properties of water. That there's some new level of description that you can use where you can throw out the really, the microscopic stuff because it doesn't depend on it anymore. And you can kind of replace that with something more convenient to work with. That's more natural to the emergent phenomenon itself. So the idea of coarse graining is that there's this idea in physics that you can take a system that has some microscopic description. So you have some kind of molecules of water, or in this case, you have some kind of grid where these things can be black or white, and they have some kind of dynamics or some kind of behavior. And then you can say, what if I zoom out? And I look at only blurry visions of the system. So I can only tell what the majority of these things are within any of these red squares. So this has more black cells than white cells. So this one just looks black when I zoom out. And then this has more white cells than black cells. So this one looks white when I zoom out. And then once I perform that procedure on the system, somehow there will be a new set of natural ways to talk about the system compared to if I had those microscopic details. So, here I might have some kind of rule that says when these things are going to be black and when they're going to be white. Here I'm going to have a new rule. And that new rule will be in terms of some new thing. And then I can continue to do this procedure in order to try to decompose the system scale by scale by scale. So I can say, this is what matters when it's very big. This is what matters when it's very small. This is what matters in intermediate scales, things like that. basically generated a whole bunch of Nobel Prizes because it allowed us to solve some very difficult physical systems when you actually use this approach. And the basic procedure is you take the full system at the present time, and then you use your model at the fine scale to predict the future, and you get some kind of future state. Then you do this coarse graining procedure, so that gets you the reduced state there. And you try to write some model that gives you a consistent future state in the coarse grain point of view. So you're not requiring this model to predict this, because it can't. You threw out the information you need to do it, but you are requiring it to predict this. This is great. It's also hard to do exactly, and unfortunately it turns out that doing it exactly is almost as difficult as actually just solving the problem directly. The almost is the reason why there were a bunch of Nobel Prizes, because even slightly less difficult is still doable in some cases where it wouldn't be doable otherwise. You can do approximations as well. But this is the idea. I'm going to talk about an application that might be a little easier to get at, which is rather than having to have this very mathematical model building exercise, which is hard to actually take to completion, what if we just approximate this? So this is actually something, this wasn't originally going to be in my talk, but I got here, I talked with a bunch of people. Specifically, I talked with Dror, and he was interested in coarse graining neurons in the brain. And there was also a talk last week that mentioned what's the light scale of consciousness. So I thought this is something that I can try to do to make this a little bit more, a little easier to contact. So the idea is that here I'm going to do this coarse graining, but I'm going to fit a neural network to it and try to use that to predict the future. And a neural network is just a sort of universal function generator. So it can make any function, and you hope that you get close to the real thing. Of course, you have finite data. But yeah.
So the fact that this thing doesn't, it's not easy to calculate what the effective rule is at the coarse scale. Maybe not the point as much as it is that it exists. You can describe the large scale dynamics with this. There exist certain local rules that describe the large scale dynamics.
Yeah. Well, I think there'll be a slide later on that'll actually get to that. So hopefully, we'll see. You can bring it up again. So the toy example, just to make sure that this idea works, is I want to just do two systems. One's going to have hard spheres. They're like billiard balls. Another is Lennard-Jones particles, which I don't want to go into a detailed description of what that means, but they're sort of like, squishy muffins. They stick to each other. They kind of compress each other. They're, if I threw these at you, you might laugh. If I threw these at you, you wouldn't laugh. And when I look at it on the small scale, you can really see a big difference here. In part, for some reason, these seem to be a lot more energetic at the small scale. I don't know why, because they should be at the same temperature, but that's how the simulation turned out. And then I can start to zoom out. And maybe you can still tell the difference between these two if you look really closely. Like here, you can kind of see maybe that these things never really overlap. They have pretty well defined, like it's blue or it's not blue. And here, it looks a little messier, but it's getting hard to see. And then at very large scale, maybe this you can't see without the lights off. Let me play it again. So there's maybe some difference in the density or like where this boundary is, but it's getting very hard to see. And if I keep going up in scale, what will eventually happen is I'll get a sharp boundary between this kind of gas state and a liquid state. And then at some other point, once this gets big enough because there's gravity, the pressure is going to be increasing, and I'll get a solid state. So I'll get a three-banded system, and it'll happen for this, it'll happen for this. I didn't have enough computer time to do that for this talk, but that's that's generic. It doesn't really care what the particles are that much. All it cares is that that they repel each other, basically, and that there's some force that's pushing them to be together. And the combination of being repelled and being pushed together, that tension is what creates the different states of matter that they fall into.